Listed are the various kinds of manifolds we'll be discussing. In Rn, we can have one-dimensional curves, two-dimensional surfaces, three-dimensional solids, all the way up to n-dimensional manifolds in Rn. For example, in R3, we have three-dimensional solids, and that's the highest possible. We're going to be interested not only in the manifolds, but in tangent spaces to the manifolds. So, for example, one-dimensional curves have one-dimensional tangent lines, two-dimensional surfaces have two-dimensional tangent planes, n-dimensional manifolds have n-dimensional tangent spaces. I don't mean to imply by the use of the word curves and surfaces that our curves need be curved. A curve can be a portion of a segment, of a line segment in Rn. Similarly, a surface can be a portion of a plane in Rn. For us, manifolds will be defined by parameterizations. Let's see how that works in the several cases. We'll start with curves, one-dimensional manifolds. Here's a curve in Rn. A parameterization of the curve is a function, x, from some segment of R1, here it is, to the curve. Here's x mapping AB to the curve. As t varies between A and B, x of t varies along the curve. Here's a neighboring point on the curve, and here's the chord between the 2 points. If h is small, then the chord is approximately tangent to the curve at P. If I divide the chord by h, its direction doesn't change. And if I take a limit as h approaches 0, the chord swings tangent to the curve, forming the tangent vector x prime of t, the limit of the chords divided by h. And here it is, tangent to the curve. X prime of t spans a one-dimensional vector space, the tangent space to the curve at P, t sub P. Next, we'll parameterize surfaces. Here's our surface S in Rn, and the parameterization is a function from a certain region of R2, because we're going to parameterize a two-dimensional manifold, a surface, to the surface. Here's Q. X maps it to a point on the surface, x of Q. As Q moves around in A, x of Q moves around on the surface. We want to now take a nearby point to Q, just as we did when we parameterized curves. But first we have to pick a certain direction, call it W. Then I'll move to a neighboring point from Q along W, and that gets me to x of Q plus HW. Here's the chord between the 2 points. The chord is nearly tangent to the surface if h is small, and if I divide this chord by h, the direction doesn't change, and if I take a limit, I get a vector which is tangent to the surface. And here it is. I can write this as the derivative at Q in the direction W. If I pick a different direction from W, call it V, I get another tangent vector to the surface at P. If I take all possible v, w, etc., I get a bunch of tangent vectors. And the fact is that those tangent vectors all lie in a single plane. That plane is called the tangent plane to the surface at P, T sub P. Finally, let's turn to the general case, the parameterization of an m-dimensional manifold in Rn. Here's the parameterization. We need a parameter space, A, which is a subset of Rm, again, because we're parameterizing an m-dimensional manifold. We need a function from x, a function x from the parameter space A to the manifold. The tangent space T sub P to M at P consists of vectors of this form. Theorem. Each of these tangent spaces is an Rm, just as for the case of two-dimensional manifolds for surfaces, each TP was a two-dimensional vector space, a plane. So far, we haven't used any geometric calculus or even geometric algebra. We've defined the notion of a m-dimensional manifold in Rn. Manifolds have vector spaces, tangent vector spaces at each point, which we've called T sub P. The tangent space is R1 for curves, R2 for surfaces, R3 for solids, etc. But the tangent vector spaces Rm extend to geometric algebra's Gm. In particular, the Gm have pseudoscalars. Recall pseudoscalars as the highest dimensional objects in Gm, vectors in G1, bivectors in G2, trivectors in G3, and so on. They form a one-dimensional vector space of Gm. This notion is essential to define the directed integral and thus to formulate the fundamental theorem. If you're not recalling pseudovectors, I suggest you go back and brush up before proceeding.